Okay, to see this result, this result analytic. So we go through the theorem one. Let's see denote any contour interior to the circle of convergence of the power series 1. Power series 1 means this. So you need to remember this power series whenever we say power series 1. And let g of g be any function that it is continuous on C. The series formed by multiplying each term of the power series by g of g can be integrated term by term over C, over the contour C. That is, we have this expression 2. Integral along to contour C, g of g times s of g dg is equal to summation n is equal to g, n is equal to 0 to infinity an times integral along to contour C, g of g times g negative g naught to the n dg. Okay, here g of g can be any function as long as it is continuous on the contour C. Okay, so for example, g of g can be a constant function. Okay, in the theorem 1, we just consider a power series like this. So this power series can be Taylor series, which is given by this, the same form, but here specifically an is defined by this f at the nth derivative of f of g naught divided by n factorial. So this theorem can be applied this Taylor series. The proof strategy is to consider two separate parts. The first is the terms of the finite sum, some finite sum, and the second is the remainder. And then we consider integral of these two parts, and we prove this integral of remainder goes to 0 as n goes to infinity. Okay, we first note that both g of g and the sum of s of g of the power series are continuous on C. This is assumption. So integral over C of the product, which means g of g times s of g, which is equal to summation n is equal to 0 to larger than negative 1 an times g of g times g negative g naught to the n plus g of g times loss of n of g. So what I'm saying, this can be split into two parts, here and here, where loss of n of g is the remainder of the given series after n terms. So the product g g of g times s of g. The integral over c of the product g of g, s of g exists. This is actually by the definition in section 42 and 44 we have learned. You need to check it. The terms of the finite sum, which means the first term here, are also continuous on the contour C. This is the polynomial multiplied by g of g, which is continuous. So their integrals over the contour C exist. This is also comes from the definition in section 42 and 44. Consequently, the integral of the quantity, the second part, must exist because two integral of two parts, this and this, exist. So the remaining part, integral of the remaining part should exist. So we can write expression 3. Integral along to the contour C, g of g times s of g dg. Summation n is equal to 0, large n negative 1, an times integral along to the contour C, g of g times g negative g naught to the n dg plus integral along to C, g of g rho n of g dg. Now let large M be the maximum value of absolute value of g on the contour C, and let large R denote the length of the contour C. In section 69, we have the uniform convergence of the given power series. We know that for each positive number epsilon, there exists a positive integer large n sub epsilon, such that for all points g on the contour C, we have this absolute value of rho sub n of g is less than epsilon whenever large n is greater than large n sub epsilon. Okay, this is definition is applied to the remainder rho n of g. Okay, since n epsilon is independent of g, this is the definition of uniform convergence. We find that this inequality whenever large n is greater than n sub epsilon, because absolute value of rho sub n of g is less than epsilon. It comes from this. And also by assumption, absolute value of g negative g of g is less than large m, because this assumption. So from these two inequality, we have this inequality. Absolute value of g times rho sub n of g is less than large m times epsilon. Then we have this from theorem in section 47, where R is the length of the contour given. So we get this whenever n large n is greater than n epsilon. That is, limit n goes to infinity, integral along to the contour C, g of g times rho sub n of g dg, is equal to 0. Because we have epsilon as small as much as possible. As small as possible. It follows, therefore, from equation 3, here, we have checked here, we have result this, as n goes to infinity, the remainder of the given power series, which means rho sub n of g, which is computed by this, which this is actually summation small n is equal to large n to the infinity an g of g an g negative g naught to the n. Okay? Its starting point is large n. So n goes to infinity. This part is equal to 0. So here, integral along to contour C, g of g times s of g dg, which is this left hand side. Limit n goes to infinity, because this part will be 0. So we get this. Okay, which is the same as equation 2 for the theorem 1. So we have proved the theorem.